Laser scanning is a really exciting piece of technology which enables us to capture the building as it is now and to create what's called a point cloud of the building, which is basically a three-dimensional dot-to-dot of the building.
When you capture a historic building like this, you're capturing it in its current state. It allows us to essentially unpick the building, so we can take the different phases out of the building because we can identify those in the point cloud and pull the building apart. I don't know if we did one and we basically just cut it in half like a cake and then just opened it out so that we could see the different layers and how the building fitted together. So we could do something like that here. Yeah, we'll be able to put cross sections right across it, see where the different floor levels are, we'll be able to see where the different window levels are, we'll be able to see where the add-ons are, just multiple possibilities. We'll just be able to disassemble it, cut it up, measure it, and basically try to understand it a lot better.
And that data is really, really useful in many ways because it creates this historical record which the design team can then use to interrogate and further their design work. But it's also gives us lots of visual imagery which we can then share with the public and we can use to communicate what's important about this building and then build on that to develop more creative digital projects later on down the line.
Laser scanning involves using a scanner like this, which will fire a laser at the surface of the building and record a 3D point in space. And it does it really quickly, so it will do hundreds of thousands of points a second, spinning around. So it'll rotate 360 degrees. The laser bounces out onto this mirror, and the mirror flips the laser around. And it records basically a series of points based on where the laser falls on the surface, any surface. So the ground, the building, the trees, everything gets recorded. What it doesn't record, of course, is what's below. So there's always a blank patch below you, a kind of a data void. So we've got an instant preview of the scan data, so we can see the building in its setting. We can see what we've captured from that station. And using this, we get an idea of where we can move to the next station to actually fill in the gaps. And what you're looking at is a simplified image of the points, and you can see the individual stones and the drains and the windows and stuff. It's a great way to record heritage and then visualize heritage, but also to take it to its ultimate use and to present it to the public. On the first pass, it's going to record I guess it's like a disto in a sense. It records distance, and then of course it knows its position in relation to itself, so then it can use trigonometry. So then what it does is it puts a single dot in space, which is a point, and you get a series of points that are being made across the surface, and that becomes a point cloud, and that basically creates the form of the building itself.
How does the scanner know where it is?
Because we have like station setups, which is where the scanner is now, and then we use these spherical targets. So they're positioned around the building, and the scanner will scan these targets, and it will recognize these targets from one scan to the next and be able to actually register the scans together. And then it will do a scan-to-scan registration, so it will look at the geometry of the building and of the wall, and it will match the geometry with the other scan, so it does a fine scan as well.
And so in an ideal scenario, you want a quiet location where there's no other people likely to be milling around?
Yeah, that's the best, so early in the morning when people are asleep. But it doesn't matter too much if people walk through, because what it will do is it just create a profile of them. So they'll just be interrupting one set of lines. So you'll see these strange profiles, which are actually people who've passed through. Cars as well pass through. So you're not going to get a full person in the way. You're just going to get a little line, a little blip.
What about weather? How do you deal with differing weather conditions?
So ideally, this is perfect. So it's a cloudy day, it's not raining, so it's perfect for photography because we've got no shadows on the building itself. Rain is difficult. Partially you don't want to put the instrument in a huge downpour, and secondly because the laser will bounce off the rain, you will get a lot of noise, so you get a lot of false points in the data, so it would look really messy. But it is possible to do it, but prefer not to.
Laser scanning is one of these technologies that has evolved massively over the last 20 years, from being incredibly expensive and probably rather cumbersome and slightly slow a process, to now being increasingly more affordable for projects such as these. The cameras being much more sophisticated, capturing things in much greater detail, and importantly sort of quicker and more accessible as well.
We started using it sort of in the early 2000s, and they were huge. They came in a I suppose you could only say like a steamer trunk, a huge box with wheels on it that you could pull. They're about the size of a traffic camera, with a huge tripod. We used to set them up. Motorists used to slow down because they used to think it was a traffic camera. They would only have like a field of like 45 degrees. So this one obviously does the 360. That would do 45, and then you'd have to turn it, and it would take probably about 45 minutes to do what this can do in 10 minutes.
Wow, so it really has advanced massively.
It's really advanced. It's got smaller, more portable. So these are some of the smallest on the market. The price has come down because they were in the 100,000 plus, and they've come down, not exponentially. They're still reasonably expensive. You're still looking at 30, 40, 50, 60,000 pounds depending on the model. You know, there's an upkeep cost as well, so you've got to have them calibrated. And the technology changes so quickly that they don't become obsolete, but the new model becomes faster, and therefore it's more profitable to have the new model than the old model because you can get more done in the same amount of time. At the end, it'll go around and take photographs, like a 360-degree panoramic photograph, and it will then add that to the points, so essentially colorize the points based on the pixels, the pixel value of the color.
By combining those two processes, what we'll end up with is a really super 3D model of the whole site, the whole building, inside and outside, which can then be used by the project team to interrogate the building as they're developing their designs, and also as part of the sort of public project that we're going to be doing, the public engagement side of things. It means we have something that we can show to the public, show to the wider audiences that we have who are interested in this building. The one issue that you have with this process is that it really does create a huge amount of data. It captures what we call billions of points of data. And what you do with those billions of points of data can sometimes be quite problematic, because lots of data is slow to view and often needs very specific software in order to be able to view it and interpret it.
The scanner isn't selective in what it records. It records everything and anything that's in its view. So it's in a line of sight instrument. So that means if that wall was completely blank, or it could be like a beautifully carved, decorative wall or something like that, it's still going to take the same amount of time and generate the same amount of data. So it's not selective at all. So I guess one of the things that you need to think about when you're doing scanning is the amount of data, because it is quite heavy. The current settings, we're scanning at about 605 megabytes per scan. So, and you think you might do 20, 30 scans, you end up with a big data set to actually work with. So you've got to think about that. And also all the data that's being collected around you, behind us, if we're only interested in the building rather than its context, that we can actually cut out to bring the file size down. We've come indoors now, and we brought the scanner in to scan this indoor space. And there's a couple of little differences that we're going to do. One, I've switched the camera off because the darkness in here. But that's fine, because the scanner's still going to be able to use the laser and actually capture the data that we need. But we're changing the resolution. So when we're outside, we've got a resolution setting that, say, maybe 3 millimeter spacing every 10 meters. So if there's an object that's 10 meters from the scanner, it'll have a 3 millimeter point density. When you bring that closer, it gets less. So you bring it to 5, and you might get a density of, say, 1.5 millimetres. So you're getting a much more dense point cloud. So if we use that outside, because we're further away from the structure, so we put a higher density in, so we take a longer scan, and that gives us a higher density of points further away. But when we're in close proximity here, we need to bring that down a bit, otherwise we're going to collect huge amounts of data on the walls that are only sort of a metre away or 2.5 metres away, so we'd be collecting sub-millimetre density point data. So we'd be really overloading the processing when we get round to processing this together. So we set that up now here in this environment. There's a set parameter for that, and we run that. So we're still going to get the intensity data, which is like the reflectivity data. So we're still going to be able to pick out the individual stones, the patterns and things. They'll just be monochrome and what we call a false colour. If we wanted to drape actual photographic textures over this scan, then we would take the scanner off and replace it with a camera and a lighting unit, and basically light it up and do a 360-degree image, and then combine that with this, rather than have the onboard camera working, because the onboard camera doesn't have the ability to basically light it up. We'll just do the full 360-degree scan, and then from that we'll be able to focus on areas such as the woodworking up there, the carvings, and then do higher density scans on those areas, and then we'll be able to produce a 3D model of that area and show the carving and the profiles, etc. We can literally zone in and basically only scan that area at super high resolution, high density. In here, in a nice and closed space where we haven't got any foliage that's moving around, I'm using the cloud-to-cloud function of the scanner, which automatically searches out for known geometry common geometry between one scan and the next scan, and automatically joins them together. Now that works in here very well because we've got our points of interest is everything. It's the full 360 degrees, the full dome. Whereas outside, our points of interest are essentially the facade of the building, and we have grass and we have trees and the wind blows through. And so the geometry changes on those objects, and it's more difficult. It's not impossible, it's more difficult to actually get the cloud-to-cloud to work outside. So that's why we use the targets outside, and why for speed and ease in these spaces I've decided to use the cloud-to-cloud. Common geometry is essentially anything that's the same in one scan to the next. So it could be a surface, for instance. So this surface here, it would recognise that surface in relation to the surface in the other, and then it recognises another surface, and it basically fits them together roughly, and then does a fine registration afterwards. And there's a point in the process where I can actually intervene if I wanted to, and actually say, okay, this point here is this point here on this scan, and it's this point there on that scan. Try again, and it will. Generally, it gets it right, and it gets it sort of sometimes better than with the targets. So we tend to do the whole thing with the targets and then do a fine cloud-to-cloud registration afterwards, because it can sometimes bring down the error factor and get everything tight together.
What do you need to know from us in order to do a good job, and in order to be able to create an end product at the end? What are the sort of conversations that you have with people?
The crucial thing in that scenario is the output. It's what do you want to do with the data? Because there might be other ways of recording the data, recording your subjects and getting data out that's more appropriate. So perhaps photogrammetry if you're after a full photorealistic product. But laser scanning is really a survey tool, and then you create. So the point cloud is very rarely given as an output. It's always used to create something else. So it might be to create a three-dimensional model, or it might be to create a set of drawings. It's up to the client, or we might use it to, like we did at Stonehenge, to analyse the stones to see if we could see any subtle features or something like that. And the same, we can do that with landscapes. So like sort of earthworks and things like that. So it does depend on what the final output is and what the project's trying to achieve as to what technology we would employ.
What we would really like to do is use the information that we capture today and that structural understanding and that historical understanding to then go away and recreate a new model using CAD software which will show us what this building looked like in its heyday, so in its medieval heyday. So what the Great Hall looked like, what the solar looked like, how the family might have decorated it, furnished it, and that will be a project that we will embark on with the local community. So we're hoping that people will use it as a sort of exciting design project, and we can go away and we can visit other sites in this local area and research things like decoration and furniture and make decisions about how we want our Calverley family to be presented at a certain point in time. A fly-through, which is basically sort of an animated video, it would take you on that journey. So in through the door, into the cross passage, which is the entry point into a medieval building, and then into the Great Hall, for example, and see the splendour of the Great Hall, the wonderful carved roof that we have there, the roaring fire, the beautiful wall hangings, the huge table that everybody gathers around and feasts at the end of the day. And then we might go and explore the solar, which is the more private end of the building, where the Lord and Lady would entertain more private guests, or where they would have their private sleeping quarters, perhaps keep their valuables, their secrets, and understand how the landscape worked around the building as well, because obviously everything that they consumed came from very nearby. So understanding that will allow us to kind of populate that world a little bit more. So that's a really, really exciting part of this whole process, is that it will lead into some interesting work that we can do with the local community that uses, cutting edge new technology. But it just goes to show that historic buildings and new technology can work together, and it's an exciting partnership between the old and the new. So that's something I'm particularly looking forward to.
Here is the scanner, and this is the scan data from it. So you can see that we've captured 360 degrees all around the room, which in this particular room is the Great Hall. And that's basically made of, so what you're seeing there isn't an image, it is a series of points. Each point receives a reflectance value, so that where the laser leaves the instrument with a certain power, and then when it returns, it comes back with less or more based on the reflection of the surface that it's bounced off. And that is then used to colour code the points, and that's why you can actually see individual bricks, individual stones, and the whole thing, and the beams, which are quite black. They've got quite dark, so a low reflection value. And you can see we can zoom right in, and it's just made of millions and millions of points that give us the data, the detail and the data that we've got. It's essentially given us a 3D model of everything it's touched. So every profile, every beam, every joist, every carving that we've got up here, it's basically captured it all that we can then use and process in the computer to help us reconstruct the building as how it was. So we'll be able to take elements of this, and where there are missing parts, we'll be able to recreate them and add them in, and that will give us a much greater accuracy to our reconstruction of the building. Not many people get to be in a space like this. They'll probably be in it when it's all done and there's a roaring fire in the place and sitting down and drinking their wine and stuff. But it's nice to actually just have some time and space with the building itself. And a building like this is kind of in its most honest form, because you can see all the repairs and all the patchwork and everything, and that's basically, you can start to read the building by looking at that. And so being able to record that is quite a privilege, I think. So I'm quite happy to be in a space like this.